All right, now that we've been introduced to the parts of an atom and some of the information found on the periodic table, let's take a closer look at the electrons. So let's focus in on some different topics discovered around electrons. So let's talk about waves. So energy moves in a wave-like pattern, and waves have several different things that we can study about them. One is wavelength. This is the length of one complete wave, so from the start to the finish of a wave, okay, and that is represented by this symbol lambda. We can also talk about the frequency, which is represented by a lowercase v. This is the number of waves that pass a point during a certain time period. So this is how many waves come by. Okay, so if you have a high frequency, then you have a lot of waves in the time period you studied. If you have a low frequency, you have few waves passing by in the amount of time that you study. We can also study amplitude. This is represented by a capital A. This is the distance from the origin to the trough or crest. So this is how high that wave is. Okay, so here is a visual representation for you. Okay, so we have a wave here. The highest point on a wave is called the crest. The lowest point on a wave is called the trough, and the center running right between the crest and the trough is known as the origin. Okay, so lambda is a wavelength, which means that you are measuring from point to point one wave. So you can measure from crest to crest, or you can measure from trough to trough. Does not matter because it is the one full wavelength. Okay, your amplitude, as you see, comes from the origin to the lowest point or the origin to the highest point. Since that origin is right in the middle, it doesn't matter which one you measure, and that is your amplitude, or how high it is. Okay, so if you have a greater amplitude, so a higher crest, this represents the intensity. And if we're talking about light, this is the intensity of the light. Or it could be for sound, okay, because sound also moves in waves. So, but the higher the amplitude, the greater the intensity. Now, frequency, looking at light, frequency is the color. So that's how our eyes detect the frequency, how often those waves come. It converts it into color for us. So different frequencies equal different colors. Okay, so this is the electromagnetic spectrum. It varies along that frequency here from low energy. On this image, low energy is over here. On the other side is the high energy. So over here is low frequency. Over here is high frequency. Okay. Now, there's only a very, very, very small spectrum of this electromagnetic spectrum that we can see visually, that our eyes can detect. There's a lot more of these energy waves that our eyes can't detect. Like, we cannot see infrared. We cannot see ultraviolet or X-rays. They exist, we just can't see them. There are some animals who can. They can sense infrared, such as snakes. Okay? But we can see this very fine area here known as the visible spectrum. And you guys have probably heard Roy G. Biv, right? The order from lowest energy to highest energy of the colors. Okay, so looking in closer at just the visual spectrum for humans, we can see that the low energy up to the high energy, and you can see it gives you an example of the frequency. See here we have a low frequency, and as you move up, the frequency increases because they get closer together. Okay. All right, so that means we can calculate, okay, because frequency and wavelength are inversely proportional. So here is another equation to add to our equation sheet. C equals lambda V. And this is one of those equations that we can put into our equation triangle to help us rearrange the equation as needed for solving the problems. Okay, so C is a constant. It is the speed of light. Okay, it never changes. So the speed of light is 3.00 times 10 to the 8th meters per second. Okay, so that is a constant. So be sure to put that on your equation sheet. This is a constant and doesn't change. C is always this number. Okay, lambda represents wavelength. Now your wavelength can be measured in any kind of length. So it could be meters, it could be nanometers, it could be kilometers. So meters. But take special notice. The speed of light's unit is meters per second. So that means in order to be able to do our equations correctly and get the correct answer, we need to always convert wavelength into meters. No matter what we were given in the equation or in the problem, we have to convert to meters so that we can, everything matches and we can cancel out. Okay? V represents the frequency. Frequency is measured in hertz. Hertz is a derived unit, and so for helping us to maintain our units, hertz is equivalent to per second. Okay, so as you can see, we have meters per second, we'll have meters, and we'll have per second. So that way we can keep up with those units to make sure we get the correct kinds of units. Okay. So if you're solving for lambda, your answer should be in meters unless it asks you to convert to something more specific. And frequency should be, you can write hertz, Hz, or you can write per second. Both will be correct, okay, because those are equivalent. So let's do a practice problem. So here's the problem. Find the frequency of a photon with a wavelength of 434 nanometers. So let's write down, what do we know from this problem? What are we given? All right, so it says find the frequency. So V is unknown. My lambda I'm given is 434 nanometers. But remember, it has to be in meters. So I'm going to use those good conversion skills that we learned earlier, and I'm going to move my decimal place the required amount of times to go from nanometers to meters so that I can have meters to use in my equation. Okay, and then C is a constant. It never changes. So I was given V and lambda, so if I look at my equation sheet to find out what equation to use, I see I need a C as well, and I wrote on my equation sheet that that is a constant that never changes. Okay? So if I use my triangle, I see that if I do not know what V is, that is my unknown, then in the triangle I have a C on top and a lambda on the bottom. So that is how I set up this equation. I do C divided by my lambda. Okay, so I put in my constant on top. I put in my lambda on the bottom in meters, and then notice we have a meters on top, we have a meters on the bottom, so those two will cancel off, and I will be left with per second. And then I just put this into my calculator. So remember to be careful with what calculator you use. For example, my cell phone calculator does not do scientific notation. But if you Google scientific calculator online, one will pop right up that you can use. And remember, to get that times 10 to the 8th, you press the E button and put in the 8. Okay? If you need help with that, get into contact with me. So we just put this into our calculator, and what do we get? 6.91 times 10 to the 14th per second. Or if you prefer to write the Hz, the hertz, you can do that too, because that's a proper frequency measurement. Those are equivalent. Okay. Now notice I have 3 sig figs here, because if I go back to my original problem, I'm only given one number, and that is 434. That has 3 sig figs. So my answer should have 3 sig figs.